Hi, my name is Shahnawaz. In this lecture, we will discuss the limit point compactness. So, we'll start with the definition of limit point compactness. Uh, Let us take a topological space X. So, we call a space X locally, we call this limit point compact if every infinite subset of X has a limit point. For example, um, let us take X to be R under the usual topology, then R is limit point compact. Similarly, if we take the closed interval, so if this is example first, let us define one more example. So um, the closed interval, so the closed interval, say 0 1, is also limit point compact. Under the usual topology. However, if we take the lower limit topology on the interval 0 1, and then it is not limit point compact. Now the limit point compactness of this real line R or this interval 0 1, so it comes from the Bolzano-Strauss theorem, which states that every bounded infinite subset of R has a limit point. So the limit point compactness follows from that theorem. However, if we take the open interval, so one can note here, and the interval 0 1 is not limit point compact. Under the usual under the lower limit topology, under the lower limit topology. So if we take, let us take one more example. So take X to be the semi-open interval, say 0 1, then this is also not limit point compact. That means there is an infinite subset of X which does not uh, have a limit point. So this is also not limit point compact. So then X is not limit point compact. For example, if we take, so for example, consider this set, say A, which contain elements of x of the form 1 over n, where n is a positive natural number, positive integer. So obviously this is a subset of x. Then clearly A does not have any limit point in x. Then A does not have any limit point in x, and hence um, it is not limit point compact. Now we will prove a result which states that the compactness always imply the limit point compactness. So we have this theorem here. Compactness, or let us state this theorem in this way. So let X be a compact topological space. Then X is also limit point compact. Let us write down the proof. So let us take X to be a compact space. So let X be a compact space. So we wish to prove X is also limit point compact. That is, every infinite subset of X has a limit point. So we wish to prove every infinite subset of X has a limit point in X. So this means that we are wishing to prove this set X is, the space X is limit point compact. So we will prove this. We will prove the contrapositive of this statement. That is, if we given a subset A of X, which uh, I mean, so we prove it is contrapositive. That is, if A has no limit point, then A is finite. That is, if A has no limit point, then A is finite. So this is one of the same thing to prove this statement or this statement over here. So mm, both will prove x is limit point. I mean, both will imply x is limit point compact. So suppose A has no limit point. So suppose A has no limit point. Now, if this is the case, then the derived set of A will be empty. So then the derived set A prime of A is empty. Now, since A prime is empty, which is contained in A, this would imply is closed. So this would imply is closed subset of X. Uh, Also, so furthermore, for each A in A, for each element A in A, we can choose a neighborhood, say UA of A, such that UA intersects A in the point A alone. Otherwise, uh, if that neighborhood intersects A at more than one point, then this A prime would not be empty. So for each A in A, we can choose a neighborhood, say UA of A, such that UA intersects A in the point A alone. Otherwise, I mean, that is UA intersection A is the singleton A. If this intersection is not singleton, suppose it contains the point A and the point B, then B will be a limit point of A. So this uh, derived set would not be empty. So therefore, this intersection has to be singleton. Uh, so that means we can cover this A by these neighborhoods. Since for each A in A we have a neighborhood, that means we can cover A by these neighborhoods. So therefore, we have an open covering so we have an open covering of A by these open neighborhoods. That is, we can write this A as union of these open neighborhoods where A is in A. Since suppose this is the set A, since for each point A in A we have this open neighborhood UA, and that means since this is true for each point in A, that means we can cover these we can cover this A by these open neighborhoods. Now, since A is closed, therefore the complement of A is open. So, since A is closed, therefore the complement of A in X, i.e., AC, is open, and hence this is open in X. Hence, this X, this will be the union of A union A complement, which is X, and this A, we can replace A by this union over here, union A complement. Now one can look at this expression over here. So this A complement is open set, then we have this union, then we have these UAs, and each UA is an open set. That means this union over here, this is equal to X. In other words, we have this expression over here. So this expression over here is the open cover of X. So that is the collection of these UAs, where A is in A, and this A complement is an open covering of X. So here we have the space X. Suppose this is A over here, so we can cover this A by these UAs. This is UA1, UA2, so on, UA. These are the open sets over here, and this is the complement of A. This is also open. So together, these UAs and this A complement, they cover the space X, but this X is given to be compact. So this open covering over here exhibits a finite subcover of X. So, but X is compact, but X is compact. So there exists a finite subcollection say A, sorry, say UA1, so on, UAN, and this A complement over here. So this finite subcollection will cover X. So among these UAs, we have these finitely many UAIs, and these UAIs, they will cover A, and this A complement will cover A complement. So together these elements, they will cover whole X. So this collection, so there is a finite subcollection which covers X, that is let's write here, that is union of these UAIs, where I goes from 1 to n, union A complement, this is X, and which is equal to A union A complement. So that means, so this further implies This further implies this union over here is actually equal to A. So therefore the union of these UAI's while I goes from 1 to n is A. But we know that each UAI intersects A in the point AI alone. So but since UAI intersection A is this singleton AI, hence if we look at this union, this is going to be the set A1 A2 through AN. So hence A would be equal to this set. So this proves A is finite. So we started at assuming that A has no limit point, and we ended up showing this A is a finite set. So that means if A is infinite, then A must contain a limit point. So this proves the uh, limit point compactness of X. So hence X is uh, hence X is limit point compact. Now we'll prove another kind of compactness that is called the sequential compactness. Now before we prove the sequential compactness, we'll first recall what do we mean by a sequence as well as a subsequence. So we now have the sequential compactness. So we'll start with the definition. So let X be a topological space. So if say Xn, where this n belongs to n, is a sequence of pointers, is a sequence of pointers in X, and if we choose randomly the positive natural numbers, say n1 which is strictly less than n2, so on, which is strictly less than say ni, which is strictly less than so on, then the corresponding terms in this sequence having these ni's as index, those terms of the sequence will form another sequence, and that sequence is called the subsequence of this sequence. So if this is an increasing sequence of positive, then increasing sequence of natural numbers, then the sequence that is called this yi defined by this yi is a n I. So this is called a subsequence of is called a subsequence of the sequence xn. So now what we mean by a subsequence, so if we have a sequence, say x1 x2 so on, say xk plus 1 so on, then from this sequence we can form the infinitely many subsequences. So suppose first let us choose this point x1 here. Now leave x2 x3 and pick suppose x4, then say x10, and suppose then x 1 million, and um, I mean pick the terms in this sequence randomly, but preserving the order. I mean first in this sequence uh, the term x1 comes first, then comes the term x4 in this sequence. So this infinite sequence um, uh, will be called, I mean this infinite sequence is also a subsequence of this sequence. So as such we can have infinitely many subsequence if we are given a sequence. So one can write an example here. Consider the sequence, say 1 1 1 by 2 2 1 by 3 3 1 by 4 4 so on. Then if we pick the terms sitting at the even places, we can get a subsequence of these numbers 1 2 3 4 and so on. Similarly, if we pick the terms of the sequence which are sitting at odd places, then we get this subsequence 1 1 by 2 1 by 3 and so on. So then the sequence, say 1 1 by 2 1 by 3 so on, is a subsequence of the given sequence. Now let us define the sequential compactness. So we have the definition. So a topological space X is said to be sequentially compact if every sequence of points of X has a convergent subsequence. Now we'll prove a theorem which states that if X is sequentially compact, then the Lebesgue number lemma holds for X. So we have this theorem over here. It states that suppose X is sequentially compact then the Lebesgue number lemma holds for x. Now, before proving this theorem, let us recall first what Lebesgue number lemma states. So, so the Lebesgue number lemma states that whenever we have, say, so whenever uh, this fancy A is an open cover of X, then there exists a delta positive such that for any subset A of X, such that for any subset S of X, such that for any subset, say, S of X, having diameter less than delta, having diameter less than delta, then there exists an element A in A that contains S, such that S is contained in A. So this is what Lebesgue number lemma states. Now let us prove the theorem. So we are going to assume the X is sequentially compact, and we'll prove the Lebesgue number lemma holds. Now to prove Lebesgue number lemma holds for X, let us pick an open cover of X first. So let A be an open cover of X. So we want to show the Lebesgue number lemma holds. So we will assume a contrary, and we will derive a contradiction. So we assume contrary, that Lebesgue number lemma does not hold for X, i.e. that is that there is no delta positive such that for each subset of X having diameter less than delta, there is an element in A containing it. Having diameter less than delta, there is an element A having diameter there is no element A in containing this subset, containing it. So therefore, for the positive integer n, so then for the positive integer n, let Sn be a subset of say Sn be a subset of x having diameter less than 1 by n, having diameter less than 1 by n. So one can note here this delta is arbitrary, so this delta may be 1 by n as well. So so our hypothesis will imply that for this positive integer n, if we pick this Sn to be a subset of x having diameter less than 1 by n, then this Sn is not contained in any of the elements in fancy A. So if we prove this Sn lies in some element A of this fancy A, then we derive a contradiction, and that will prove that such a delta exists. So let us take a point. So take say xn in Sn. So we can do this for any n. So this n is not fixed here. So this n may be anything. So this n may be 1, 2, 3. So if n is 1, then we have a point x1 in S1. So if n is 2, then we have a point x2 in S2, where S2 has diameter less than half, and in general Sn has a diameter less than 1 over n. So therefore in this way we get a sequence. So therefore in this way we get a sequence xn of points in x. Such that where xi is in the set Si and diameter of Si is less than 1 over I. Now x being sequentially compact, then this sequence may have a subsequence which is so we can write this down here. Now x being sequentially compact, the sequence xn has a convergent subsequence. Say xni, where this I is some natural number. So now this subsequence being convergent means there is some point x in x to which this subsequence mm, converges. So let the subsequence x and I converges to x for some x in x. Now we have chosen this A to be a covering of x. So that means this x may may lie inside some element A of this fancy A, because this fancy A covers x. So since this fancy A covers x, this point x may lie inside A for some A in fancy A. Now, so let us draw a picture over here. So let this be the element A of this fancy A, and this x is a point somewhere here. So now this A being an element of fancy A, so it is an open set. So this must be a neighborhood of this point x in A. So but A being open, A is therefore a neighborhood of fancy x. Hence, there exists uh, an open ball centered at x. So, since hence we may choose some epsilon bigger than 0 such that the ball centered at x and radius epsilon is contained in A. So that means we have a ball inside A which contains the point x. So let us use the ball x bx epsilon. So I forgot here. This x is metrizable space. In this x, so suppose x be a metrizable sequentially compact space, then the Lebesgue number lemma holds for x. So why do we need metrizability? Because the metric will induce this ball around this point over here. So now let us choose. So let us choose I large enough so that 1 by n sub I is less than epsilon by 2, and uh, the distance of x and I from x is less than epsilon by 2. So if distance of x and I from x is less than epsilon by 2. Since this distance is epsilon, so x and I may be a point near x and I at a distance less than epsilon by 2. Now since diameter of diameter of S and I is uh, less than 1 by Ni, and this 1 by Ni is less than epsilon by 2. That means this S and I mean, and let us first write over here, and X and I is inside S and I. So then the set S and I lies in the epsilon by 2 neighborhood of X and I. So there is an epsilon by 2 neighborhood of X and I, which contains this set. So this is the set S and I. So this S and I has diameter less than epsilon by 2, and this ball over here, this ball is centered at X and I, and it has radius epsilon by 2. So then uh, the set S and I lies in the epsilon by 2 neighborhood of X and I. Now one can note here, now this S and I, this is contained in the ball centered at X and I, and radius 1 by Ni, which is less than epsilon by 2. So this is contained in the ball centered at X and radius epsilon. So one can note over here, and this ball is contained inside A. So we proved for this subset S and I of X, there exists an element A in fancy A such that this A contains this element. So this proves, and so this is the contradiction to our hypothesis, because we assumed at the first place that there is no such delta for which the Lebesgue number lemma is true. So which is a contradiction to our hypothesis. So this proves our hypothesis is wrong. So hence Lebesgue number lemma holds for the space X.